This is Saturn. Why Saturn's rings are disappearing. 1.4 billion kilometers from the Sun, in the frigid and dim outskirts of our solar system, lies a planet adorned with a crown of ice. This crown spans an astonishing 282,000 kilometers from one edge to the other, wide enough to bridge the gap between Earth and the Moon. Yet it is remarkably thin. In certain areas, the main rings measure no more than 10 meters in thickness. If you were to compress Saturn's rings to the size of a football field, they would be thinner than a razor blade. Such an improbable structure, vast beyond imagination, yet delicate beyond belief. Imagine standing within the rings, gazing around, floating among the particles in the B ring, for instance. You would witness an extraordinary vista. Not an empty void, but a dense, gently shifting field of ice boulders, varying from the size of a snowball to that of a house, all drifting together in a synchronized dance, moving in roughly the same direction and at a similar speed. The relative velocities between neighboring particles are minuscule, mere millimeters per second, akin to a slow heartbeat. They gently collide, rebound, and spin languidly, catching the faint sunlight and scattering it in every direction. Above and below, the rings would stretch to the horizon, a flat, shimmering expanse of ice, impossibly thin, extending farther than the eye can see. Saturn would loom large in the sky, its banded atmosphere occupying a significant portion of your field of vision, its curvature apparent, its weather systems discernible. The distant and dim sun would illuminate the rings from the side, casting sharp shadows from each particle, shadows that would glide across their neighbors as the rings orbit the planet. You would be enveloped by water ice, the most abundant molecule in the outer solar system, formed in the same molecular clouds that birthed the Sun, older than the rings themselves, older than Saturn, perhaps even older than the solar system. This ice carries memories of conditions that no longer exist anywhere else in this part of the cosmos, and it is slowly, grain by grain, drifting inward, toward the planet that will ultimately consume it. Composed of billions upon billions of particles of water ice, ranging from grains of sand to house-sized boulders, all orbiting the planet in a flat, glimmering disk. For 4 centuries, since Galileo first observed something peculiar about Saturn's shape through his early telescope in 1610, the rings have come to define the planet. They are the most recognizable feature in the solar system, the one image that, shown to any human on Earth, would be instantly recognized. They are breathtaking, they are iconic, and they are fading away. Saturn's rings are not ancient remnants from the dawn of the solar system. They are young, astonishingly, almost unbelievably young. The most recent evidence gathered from the final orbits of NASA's Cassini spacecraft suggests that the rings are no more than 10 to 400 million years old. When the most colossal dinosaurs roamed the Earth, Saturn may not have had its rings at all. When Tyrannosaurus rex prowled the forests of what is now Montana, the rings may have been in the process of forming, or perhaps already in decline. The iconic feature that characterizes the planet is a transient phenomenon, a fleeting adornment on a 4.5 billion-year-old world. And the rings are vanishing. Right now, as you listen to this, ice particles from Saturn's rings are cascading into the planet's atmosphere, drawn inward by gravity and guided along magnetic field lines, falling at a rate that drains enough water to fill an Olympic-sized swimming pool every half hour. At this pace, the entire ring system will be gone in 100 to 300 million years. Saturn will revert to being the bare gas giant it was for the majority of its existence. We find ourselves in a fleeting moment, a rare window in the 4.5 billion-year saga of our solar system, where Saturn dazzles us with its magnificent rings. This window opened less than 400 million years ago and will soon close, perhaps within a few 100 million years. Once it does, no future civilization or distant observer will ever witness Saturn as we do today. Tonight, we embark on a journey to explore the life and eventual demise of Saturn's rings. From their tumultuous origins, possibly born from the cataclysmic destruction of a moon or the disintegration of a comet, to their gradual, inevitable decay as they spiral into the planet that birthed them. We'll delve into the Cassini mission that unveiled their youthful splendor, the physics that foretells their demise, the moons that guide and shape them, and the forces that are pulling them apart. For Saturn's rings are not just a breathtaking spectacle, they are a cosmic clock, and time is running out. Be sure to subscribe, as there are countless more extraordinary tales from the cosmos waiting to be uncovered. Saturn itself is a realm of astonishing scale and peculiarity, even without its iconic rings. As the second largest planet in the solar system, it boasts a mass 95 times that of Earth and a diameter of 120,536 kilometers, making it 9.5 times wider than our home planet. Like Jupiter, Saturn is primarily composed of hydrogen and helium, with a small yet significant proportion of heavier elements. However, Saturn diverges from Jupiter in several crucial aspects. First, consider its density. Saturn is the least dense planet in the solar system, with an average density of about 0.687 grams per cubic centimeter, lighter than water. This leads to the intriguing thought experiment: if you could find an ocean vast enough, Saturn would float. While this statement is physically accurate, it is practically absurd. Saturn's low density arises from its composition, predominantly hydrogen and helium, the lightest of elements, and its relatively modest mass. Jupiter, being 3 times more massive, is compressed to a higher density by its own gravitational pull. In contrast, Saturn, being less massive and less compressed, expands outward, occupying more volume per unit of mass than any other planet. Next, we have its shape. Saturn is the most oblate planet in the solar system, flattened at the poles and bulging at the equator by about 10%. This phenomenon results from its rapid rotation. A single day on Saturn lasts just 10 hours and 42 minutes, coupled with its low density. The centrifugal force at the equator pushes material outward, distorting the planet into a distinctly non-spherical form. Through a telescope, this flattening is readily observable. Lastly, let's explore its internal heat. Like Jupiter, Saturn emits more energy than it absorbs from the Sun, approximately 1.8 times more. However, the source of Saturn's excess heat may differ from that of Jupiter. While Jupiter's heat primarily stems from ongoing gravitational contraction via the Kelvin-Helmholtz mechanism, Saturn might have an additional source: helium rain. Deep within Saturn's core, at pressures reaching millions of atmospheres, helium becomes less soluble in hydrogen. This helium separates out, forming droplets that cascade downward through the metallic hydrogen ocean toward the core. As these dense helium droplets descend, they release gravitational potential energy in the form of heat, an analogous process to the hypothesized diamond rain within Neptune, but involving helium instead of carbon. This fascinating differentiation of helium has tangible implications. Saturn's atmosphere is notably lower in helium compared to both the solar standard and its giant neighbor, Jupiter. The helium has descended, effectively raining out of the atmosphere and accumulating in the planet's depths. This phenomenon of helium rain is a process of extraordinary intricacy. At the extreme temperatures and pressures found deep within Saturn, millions of atmospheres and thousands of degrees, hydrogen and helium behave as quantum fluids, adhering to the principles of condensed matter physics rather than classical chemistry. Under these conditions, helium becomes immiscible in metallic hydrogen. The two elements separate, much like oil and water, despite having been blended since the planet's inception. Helium forms dense, heavy droplets that sink through the metallic hydrogen ocean, driven by gravity. As each droplet of helium descends, it releases a minuscule amount of gravitational potential energy. When considered across the vast expanse of Saturn's interior over billions of years, this process generates a substantial amount of heat. It operates as a slow, patient furnace, a planet gradually warming itself through the settling of one element into another. The observation of helium depletion in Saturn's atmosphere stands as a pivotal piece of evidence supporting the helium rain hypothesis. This phenomenon may also elucidate why Saturn radiates a greater proportion of excess heat compared to Jupiter. The rain serves as an additional energy source that Jupiter, with its distinct internal conditions, may not possess. Saturn's magnetic field, while weaker than Jupiter's, is still an impressive 578 times stronger than Earth's. Uniquely among the planets, Saturn's magnetic field is almost perfectly aligned with its rotation axis. The tilt between the magnetic and rotational poles is less than 0.01 degrees. This near-perfect alignment presents a theoretical conundrum, as dynamo theory suggests that a purely axisymmetric magnetic field should decay over time rather than maintain itself. Some mechanism must be obscuring the true complexity of Saturn's internal magnetic field, potentially a layer of helium rain that functions as a conducting shell, smoothing out any non-axisymmetric components before they reach the surface. If this helium rain layer exists, it would represent a distinctive characteristic of Saturn's interior, a conducting barrier between the deep dynamo and the surface, filtering the geometry of the magnetic field. No other planet is known to possess such a feature. Like Jupiter, Saturn's interior is believed to consist of an outer layer of molecular hydrogen, transitioning to metallic hydrogen at greater depths, with a core of heavier elements at its center. However, Cassini's gravity measurements during the grand finale revealed that Saturn's winds penetrate much deeper into its interior than those of Jupiter, extending to a depth of approximately 9,000 kilometers, or about 15% of the planet's radius. This is 3 times deeper than the corresponding depth on Jupiter. The discovery of this deep rotation was unexpected and suggests that Saturn's interior is less rigidly structured than that of Jupiter. The transition from a differentially rotating atmosphere to a uniformly rotating interior occurs at a much greater depth. The core itself, much like Jupiter's, may be more dilute than compact, a region characterized by a gradual increase in heavy element concentration rather than a sharply defined rocky sphere. The total mass of heavy elements within Saturn's interior is estimated to be between 15 to 18 Earth masses, aligning with earlier theoretical predictions. However, the distribution of these elements, how much resides in the core versus how much is mixed into the envelope, remains an active area of research. And then there's the hexagon. At the North Pole of Saturn, a remarkable 6-sided jet stream wraps around the pole, forming a hexagonal atmospheric feature that spans approximately 30,000 kilometers, its sides longer than Earth's diameter. This hexagon has been continuously observed since the Voyager flybys in 1980 and 1981, enduring for over 4 decades. Its unique shape arises from the dynamics of a jet stream oscillating at a specific wavelength, which creates a 6-fold symmetry, a phenomenon that can be replicated in laboratory fluid dynamics experiments. Yet its enduring nature, stability, and flawless geometry stand out as some of the most extraordinary atmospheric phenomena in our solar system. The history of observing Saturn stretches back thousands of years. It is the most distant planet visible to the naked eye, a fact that granted it a distinguished place in ancient astronomy. For the civilizations of Mesopotamia, Greece, and Rome, Saturn marked the boundary of the known universe. Beyond it lay nothingness, only the fixed stars, believed to be embedded in a crystalline sphere at the edge of existence. Saturn was the sentinel of this boundary, the guardian of the outermost gate. This connection to limits and frontiers is, in hindsight, quite fitting. Saturn occupies a pivotal position in the solar system, at the outer edge of the region where the giant planets formed, beyond which the ice giants Uranus and Neptune represent an entirely different class of worlds. The formation of Saturn, much like that of Jupiter, was a race against time, a competition to gather enough gas from the solar nebula before the disk dissipated. Saturn emerged victorious, albeit narrowly, capturing less gas than Jupiter and settling at 95 Earth masses instead of 318. Had Saturn been just a bit more massive or formed slightly earlier, it might have rivaled Jupiter in size. Conversely, had it been a touch less massive, it could have ended up as an ice giant. Saturn is also the planet that, according to the Grand Tack hypothesis, preserved the inner solar system. When Jupiter migrated inward toward the Sun in the early years of the solar system, it was Saturn's formation and subsequent movement that created the orbital resonance necessary to reverse Jupiter's trajectory. Without Saturn, Jupiter would have continued its inward journey, transforming into a hot Jupiter and obliterating any chance for terrestrial planets to form. Saturn acted as the brake, the counterweight, the planet that halted Jupiter and pushed it back outward, safeguarding the inner solar system for the emergence of Earth. Saturn is a faint, yellowish point of light that drifts slowly against the backdrop of stars, taking 29.4 Earth years to complete a single orbit. The Babylonians tracked its movements. The Greeks named it Kronos, the father of Zeus. The Romans referred to it as Saturn, the god of agriculture and time. The association with time is particularly apt. Saturn moves so slowly that it seems to preside over the ages. When Galileo first trained his telescope on Saturn in 1610, he perceived what appeared to be a planet with two companions, handles or ears flanking either side. 2 years later, those companions had vanished. Saturn had tilted its rings edge-on to Earth, rendering them invisible. Galileo was perplexed. Had Saturn devoured its children like the mythological deity? The mystery remained unsolved until 1655, when Christian Huygens, using a more advanced telescope, discovered that Saturn was surrounded by a flat ring, inclined to the ecliptic, which appeared to disappear when viewed edge-on and re-emerged as the angle shifted. In 1675, Giovanni Cassini uncovered the dark gap in the rings that now bears his name. In 1859, James Clerk Maxwell mathematically demonstrated that the rings could not be solid or liquid. They must consist of countless small particles, each orbiting independently. This was a triumph of theoretical physics. Maxwell predicted the structure of the rings solely through calculation, decades before any telescope could confirm his findings. Saturn is a planet of extremes and curiosities, a title it holds even before we delve into the splendor of its rings. Yet, it is these very rings that define Saturn's identity. Understanding their origin, age, structure, and ultimate destiny has become a cornerstone of planetary science. Through even a modest telescope, one no more powerful than Galileo's, Saturn's rings emerge as a striking, luminous halo. They are among the most rewarding sights for amateur astronomers, visible even from light-polluted urban landscapes. With a larger telescope, the Cassini division reveals itself as a slender, dark line. Subtle color variations between the rings come to life. The B ring shines slightly brighter and whiter. The A ring takes on a hint of grey, while the C ring presents a ghostly translucence against the planet's surface. When the rings are tilted at their maximum angle, approximately 27 degrees, they appear vast and majestic. Conversely, when they are edge-on, as they were in 2009 and will be again in 2025, they nearly vanish, reducing Saturn to a simple, oblate sphere with a delicate line bisecting it. The ring plane crossing in 2025 will make the rings nearly invisible to all but the largest telescopes, a glimpse, in a way, of what Saturn will look like in a few 100 million years when the rings are permanently gone. For a brief period, observers will witness Saturn devoid of its rings. Yet, as the tilt increases once more, the rings will re-emerge, and the planet will reclaim its iconic, familiar visage for just a little while longer. For those who have yet to gaze upon Saturn through a telescope, now is the moment. Not because the rings are on the verge of vanishing tomorrow, they will endure for millions of years to come, but because there will come a time, far in the future, when they will be lost. And those who encounter Saturn in that distant era will remain unaware of what they are missing unless we share this knowledge with them. For much of astronomical history, Saturn's rings were believed to be ancient, dating back to the planet's formation, composed of the same material that coalesced into Saturn 4.5 billion years ago. This notion seemed logical. The rings are immense, stable, and seemingly eternal. They have been observed for 4 centuries without any apparent change, appearing as a primordial feature, a remnant of the solar nebula, a leftover from the gas and dust disk from which Saturn formed. This assumption, however, was flawed. The first significant challenge arose from theoretical insights. In the 1980s and 1990s, physicists noted that Saturn's rings should darken over time due to the accumulation of interplanetary dust, tiny particles of rock and organic matter that rain down through the solar system from asteroid collisions, cometary activity, and the Kuiper belt. Pure water ice, when freshly exposed, is bright and reflective. Over time, the steady influx of dark, non-icy material should contaminate the ice, diminishing its brightness. If the rings were indeed 4.5 billion years old, they should appear much darker than they do. The observed brightness suggested that the rings were either very young or were being continuously replenished with fresh ice. The second challenge stemmed from dynamics. Saturn's rings are not static. They are a collisional system, particles perpetually colliding, exchanging energy and angular momentum. These collisions cause the rings to spread over time, akin to a deck of cards being pushed outward on a table. If left unchecked, this viscous spreading would lead to the rings dissipating, the inner material spiraling into the planet, the outer material drifting away. For the rings to have persisted for 4.5 billion years, some mechanism would need to continuously counteract this spreading. While shepherd moons do help confine some of the narrower rings, no mechanism has been identified that could sustain the entire main ring system for billions of years against this viscous dispersion. The third and most definitive challenge came from the Cassini mission. During its final mission phase, the grand finale 2017, the Cassini spacecraft executed 22 daring dives between Saturn and its innermost ring, skimming just 2,600 to 3,900 kilometers above the planet's cloud tops. On 6 of these thrilling passes, Cassini established a precise radio link with Earth, enabling scientists to measure the gravitational influence of both Saturn and its rings with remarkable accuracy. For the first time, they disentangled the gravity of Saturn from that of its rings, allowing them to determine the ring's mass. The findings were nothing short of astonishing. The total mass of the rings is approximately 1.54 times 10 to the power of 19 kilograms, about 0.41 times that of Saturn's moon Mimas, which is itself 2,000 times smaller than Earth's moon. The rings are surprisingly light, far less massive than previous estimates had suggested. This low mass indicates youth, as a more massive ring system, subjected over time to meteoroid bombardment and viscous spreading, would have diminished to this mass only after a few 100 million years. In a separate study published in Science Advances in May 2023, physicist Sascha Kempf and his team at the University of Colorado Boulder presented what they termed the strongest evidence yet. Utilizing the Cassini Cosmic Dust Analyzer, the team dedicated 13 years, the entire duration of Cassini's mission at Saturn, to collecting dust grains in the vicinity of the rings. They captured a total of 163 grains that originated from beyond the Saturn system, interplanetary dust drifting in from the broader solar system. From these 163 meticulously gathered grains, they calculated the rate at which interplanetary dust accumulates on the rings. The method is elegantly simple. Imagine dating a house by the dust on its shelves. A new house has pristine shelves, while an old house is coated in thick layers of dust. By measuring how quickly dust accumulates and how much dust is currently present, one can estimate how long the shelves have been exposed. In this analogy, the rings of the shelves and the interplanetary dust, micrometeoroids from asteroid collisions, cometary debris, and Kuiper belt material, represents the dust. The contamination level of the rings, the proportion of non-ice material mixed into the ice particles, reflects the thickness of the dust layer. Kemp's team directly measured the infall rate using Cassini as a dust collector and compared it to the observed contamination. The conclusion was clear. The rings have been collecting dust for only a few 100 million years. They are pristine because they are young. This result beautifully aligns with the mass measurement from the grand finale gravity science. A low mass suggests youth, as a more massive, older ring system would have lost mass over time through viscous spreading and meteoroid bombardment, reaching its current low mass only after several 100 million years of erosion. Additionally, both findings converge with the brightness argument. Older rings should appear darker. Saturn's rings, however, are bright. They shine brightly because they are young. Three independent indicators, dust, mass, brightness, all point to the same conclusion. The answer is less than a gram per square foot per year. A light sprinkle, but enough to accumulate over time. By comparing the measured dust flux with the observed contamination levels in the rings, they concluded that the rings have been accumulating dust for no more than a few 100 million years. The rings are indeed young. Three independent lines of evidence, the brightness of the ice, the low mass determined through gravity science, and the dust accumulation rate, all converge on the same conclusion. Saturn's rings formed between approximately 10 and 400 million years ago. The most frequently cited range is 10 to 100 million years. The rings are younger than the dinosaurs. They are younger than the Atlantic Ocean. They may even be younger than the Rocky Mountains. To fully grasp the magnitude of this revelation, let's delve into its implications. For an astonishing 4.1 to 4.4 billion years, approximately 90 to 98% of Saturn's lifespan, the planet existed without a prominent ring system. Imagine traveling back to the age of dinosaurs, peering through a telescope at Saturn and witnessing a bare, banded gas giant devoid of any visible rings, or perhaps just a faint, nascent disk of debris. The Saturn that Galileo observed, the one that Cassini meticulously explored, the iconic planet that graces every child's textbook. This version of Saturn has only been around for less than 1/10 of the planet's entire history. It is not the true Saturn. It is merely a fleeting costume the planet dons for a brief chapter in its long saga. This groundbreaking discovery shatters a century's worth of established beliefs. Textbooks that once depicted the rings as ancient, primordial features are now being rewritten. The focus has shifted from the question, how have the rings persisted for 4.5 billion years, to a more intriguing inquiry, what catalyzed their formation so recently? The former question always left us wanting, relying on explanations that lacked robust observational backing. In contrast, the answer to the latter question is both dramatic and precise. A moon was destroyed. This revelation is unexpected and prompts a profound inquiry. If the rings are indeed young, what brought them into existence? The prevailing hypothesis is both violent and specific. The rings formed from the cataclysmic destruction of a moon. Saturn's gravitational influence establishes a boundary known as the Roche limit, the distance within which tidal forces overpower the self-gravity that binds a celestial body. For an icy object near Saturn, This Roche limit is approximately 140,000 kilometers from the planet's center. Within this zone, an object cannot maintain its structural integrity. The tidal forces exerted by Saturn will stretch, crack, and ultimately disintegrate it. If a moon, or a comet, or a Centaur object from the outer solar system were to stray within Saturn's Roche limit, it would face obliteration. The resulting debris would disperse into a disk, colliding, grinding, and gradually coalescing into the thin, orderly ring structure we observe today. This transformation would unfold over thousands to millions of years, as the chaotic cloud of debris settled into a smooth disk through countless gentle collisions. The mass of the current rings, approximately 0.4 times that of Mimas, aligns with the destruction of a moon roughly the size of Mimas itself, about 400 kilometers in diameter, or perhaps slightly larger, with some mass inevitably lost to Saturn's atmosphere during the initial disruption and the subsequent evolution. In 2022, a study spearheaded by Jack Wisdom at MIT proposed a striking and detailed scenario. Utilizing new measurements of Saturn's axial tilt, 26.7 degrees, unusually pronounced for a gas giant, the team posited that Saturn once hosted an additional large moon, dubbed Chrysalis. This moon orbited Saturn for billions of years in a stable configuration. However, gravitational interactions with Titan, Saturn's largest moon, gradually destabilized Chrysalis's orbit. At some point, possibly 100 to 200 million years ago, Chrysalis ventured into a chaotic orbital zone, drew perilously close to Saturn, and was ultimately torn apart by tidal forces. The destruction of Chrysalis would have achieved two significant outcomes simultaneously. First, it would have generated the debris that coalesced into the rings. Second, the loss of this moon would have altered Saturn's gravitational dynamics, liberating the planet from a spin-orbit resonance with Neptune that had previously dictated its axial tilt. The current tilt of Saturn, slightly deviating from the resonance value, suggests a recent departure from this resonance, triggered by the loss of a moon. The Chrysalis hypothesis captivates us with its elegance, as it elegantly ties together the youth of Saturn's rings and the planet's tilt through a singular, cataclysmic event. Yet, it is not the sole contender. Alternative theories suggest that the rings could have originated from the destruction of a smaller moon, perhaps due to a collision with a massive comet or Centaur, or even from the tidal disruption of a Kuiper belt object that ventured too close to Saturn. The true genesis of these magnificent rings remains shrouded in mystery. What we do know is that they are not ancient relics. Rather, they were forged in the fires of a violent episode in Saturn's relatively recent history. There's a certain poetic resonance to the Chrysalis hypothesis. The notion that Saturn's stunning rings emerged from the loss of a moon, that the most breathtaking feature of the most beautiful planet was born from chaos, echoes a deeper truth about our solar system. Many of the most awe-inspiring characteristics we observe are the aftermath of catastrophe. Earth's moon was birthed from a colossal impact. The asteroid belt was sculpted by Jupiter's gravitational fury. Mars's diminutive size is a byproduct of Jupiter's migration, and Saturn's rings, the most iconic visual hallmark in planetary science, may very well be the remnants of a world that was violently torn asunder. If Chrysalis did exist, if there was once a moon orbiting Saturn in the space between Titan and Iapetus, perhaps half the size of the current moon Dione, residing in a region devoid of large moons today, then that moon would have undergone billions of years of orbital evolution before its ultimate catastrophic encounter with Saturn's tidal forces. The dynamics of its destruction would have been nothing short of spectacular. As Chrysalis crossed into the Roche limit, Saturn's tidal forces, the gravitational disparity between the moon's near and far sides, would have overwhelmed the moon's own self-gravity. Initially, cracks would have spiderwebbed across its surface. Next, the Moon would have elongated, stretching into a cigar-like shape aligned with Saturn's pull. Ultimately, it would have shattered, breaking apart into thousands, then millions, and eventually billions of fragments, each following its own orbit around Saturn. The initial debris cloud would have been a chaotic spectacle, a thick, turbulent torus of ice and rock, colliding and grinding, filling a vast expanse of Saturn's orbital domain. Over thousands of years, this debris would have flattened. Collisions between particles dissipate energy while conserving angular momentum, resulting in a flat disk, the minimum energy configuration for a system of orbiting particles. The disk would have continued to thin, with particles grinding against one another, larger fragments fracturing into smaller ones until the rings achieved something akin to their current form. A thin, flat, ordered disk of ice particles gracefully orbiting in Saturn's equatorial plane. This entire transformation, from the Moon's destruction to the emergence of a recognizable ring system, might have unfolded over a few million years. Rapid by geological standards, yet instantaneous in the grand scale of the cosmos. It formed alongside Saturn, orbited serenely for eons, and was gradually nudged into instability by Titan's gravitational embrace. Its demise was a slow burn, yet its execution was swift. And from this demise arose the rings, a crystalline memorial to a world that has long since vanished. The chrysalis hypothesis, while intriguing, is not without its detractors. Some scientists have raised doubts about whether a moon of the necessary size could have maintained dynamic stability for billions of years before being nudged into chaos. Others suggest that the rings might have originated from the tidal disruption of a passing centaur, an icy object from the far reaches of our solar system, rather than the demise of a native moon. A study conducted in 2024 even challenged the notion of young rings, proposing that a phenomenon known as ring rain pollution ejection could create the illusion of youth in older rings by continuously expelling contaminated material and revealing fresh ice beneath. In this scenario, the rings could be ancient, yet retain their dazzling brightness by actively shedding darker debris. The discussion remains unresolved. However, the accumulating evidence, including the rings' low mass, high brightness, measured dust flux, and dynamic models, leans towards a more recent origin. It seems increasingly likely that the rings are a fresh addition to Saturn's ensemble, born from a cataclysm and destined to fade away. From the ashes of its demise arose the rings, a frozen tribute to a world that has vanished. One thing is clear: these rings are not primordial. They were forged in the fires of a violent event in Saturn's relatively recent history. But the rings are not just young, they are in decline. The concept of ring rain first emerged in the 1980s when images from Voyager 2 unveiled narrow dark bands in Saturn's upper atmosphere at northern mid-latitudes. In 1986, Jack Conany at NASA's Goddard Space Flight Center proposed that these bands resulted from water cascading from the rings into the atmosphere along magnetic field lines. Composed of water ice, the rings are perpetually bombarded by ultraviolet radiation from the sun and micrometeoroid impacts which ionize the ice particles, stripping away electrons and generating charged water molecules. These charged particles are subsequently captured by Saturn's magnetic field, which directs them along field lines into the atmosphere at specific latitudes. Observations made with the Keck telescope confirmed the existence of ring rain and quantified its rate. The findings, published in 2018, were startling. James O'Donoghue, the lead author of the study, estimated that the ring rain drains enough water to fill an Olympic-sized swimming pool every half hour. At this pace, the entire ring system could vanish in approximately 300 million years. Yet ring rain is not the sole mechanism depleting the rings. Cassini's final dives detected an additional, more significant flow of material plummeting from the innermost D ring directly into Saturn's equatorial atmosphere, at rates reaching up to 10,000 kilograms per second. This equatorial inflow, combined with the magnetic ring rain at higher latitudes, results in a total mass loss rate that could exhaust the rings in under 100 million years. The physics at play is unyielding and irreversible. Micrometeoroids from the Kuiper belt relentlessly bombard ring particles. Each impact ejects fragments and generates charged particles. These fragments, smaller and more vulnerable to drag forces, spiral inward. The charged particles are funneled along magnetic field lines. Material flows from the outer rings to the inner rings, and from the inner rings to the planet itself. The rings function as a conveyor belt of ice, steadily feeding themselves into Saturn's atmosphere. This process is irreversible. There is no mechanism to replenish the rings. Once the ice is lost, it is lost forever. The material that rains down into Saturn's atmosphere vaporizes in the upper layers, where it mingles with hydrogen and helium. Cassini's final dive through this region detected water, methane, ammonia, carbon monoxide, molecular nitrogen, and carbon dioxide, all sourced from the rings. The chemical signature of the infalling material confirmed that the rings are indeed the origin. Saturn is consuming its own rings, and the feast is nearly halfway done. The phenomenon of ring rain around Saturn is anything but static. It ebbs and flows in tandem with the planet's seasons, each lasting approximately 7.4 Earth years due to Saturn's lengthy orbital period of 29.4 years. As Saturn orbits closer to the Sun, the intensity of ultraviolet radiation surges, leading to the ionization of more ring particles and consequently accelerating the rate of rain. During the equinoxes, when sunlight strikes the rings at a sharper angle, the dynamics of ring rain shift, altering the latitudes where material descends into the atmosphere. This intricate system of rings is in constant flux, reacting to the changing geometry of Saturn's orbit, the strength of the solar wind, and the relentless bombardment of micrometeoroids from the Kuiper belt. Each of these elements plays a crucial role in the ongoing erosion of the rings. O'Donoghue paints a striking picture. Envision a bathtub gradually draining, devoid of a faucet to replenish it. The water level consistently declines. At times, the drain accelerates during storms or seasonal transitions, while at other moments it slows. Yet the trajectory remains unwaveringly downward. The tub is perpetually losing water, and inevitably it will run dry. In a pair of studies published in Icarus in 2023, Richard Durazan and Paul Estrada explored the long-term evolution of Saturn's rings, factoring in the effects of viscous spreading and micrometeoroid impacts. Their simulations revealed that even the colossal rings, those as substantial as Saturn's at its inception, cannot endure for more than a few 100 million years, given the current rate of meteoroid influx. The rings are gradually worn away, eroded, and pulled inward on a timescale that pales in comparison to the age of the solar system. Estrada offered a sobering forecast. The sparse, delicate rings observed around Jupiter, Uranus, and Neptune may very well be the remnants of once magnificent ring systems that rivaled Saturn's in grandeur. Those rings have already been diminished. Now Saturn's rings are next in line. The innermost rings are poised to vanish first. The D ring, which is closest to the planet, is already fragile and fading. Following it will be the C ring, characterized by its lower density. The massive B ring, the densest and brightest of all the main rings, containing roughly 2/3 of the total ring mass, will endure the longest. Its opacity is such that it obstructs nearly all light, casting a profound shadow on Saturn's cloud tops during equinox. The structure of the B ring is extraordinarily intricate, featuring thousands of narrow ringlets whose spacing and density fluctuate in patterns that remain partially enigmatic. Some of these formations may be self-organizing, arising from the ring's own gravitational and collisional dynamics, creating order without the influence of any external moons. The A ring, being thinner and less massive, will succumb to erosion more rapidly. It is separated from the B ring by the Cassini division and extends outward to the Roche division, beyond which lies the F ring. The A ring is home to the Encke and Keeler gaps, the propeller moonlets, and density waves driven by resonances with Mimas, Janus, and Epimetheus. Its outer edge is sharply delineated by a 7-6 resonance with the moons Janus and Epimetheus, a resonance so precise that it maintains a distinct boundary in an otherwise diffuse system. The C ring, the innermost of Saturn's main rings, affectionately dubbed the crepe ring for its delicate, translucent appearance, stands out as the most contaminated and least massive of them all. It is likely to be the first to vanish completely, its icy particles gradually ground down and absorbed into Saturn's atmosphere over the next few tens of millions of years. Just beyond it lies the D ring, a mere whisper of a ring that is barely detectable even by Cassini's sophisticated instruments. Yet, even this faint structure cannot withstand the relentless forces of erosion indefinitely. In the coming 100 to 300 million years, Saturn's rings will thin, darken, and ultimately fade away. The planet will slowly lose the iconic feature that has defined its grandeur, and when the last ice particle spirals into Saturn's atmosphere and vaporizes, the solar system will bid farewell to one of its most exquisite formations. These rings are not simply a static disk of ice. They represent one of the most dynamically intricate structures in our solar system. The main rings, designated A, B, and C in the order of their discovery, are composed of thousands of individual ringlets, separated by gaps of varying widths. The most prominent of these gaps, known as the Cassini division, stretches an impressive 4,800 kilometers and separates the A and B rings. Discovered in 1675 by Giovanni Cassini using a refracting telescope, it was long believed to be devoid of material. However, Cassini revealed that this division is not empty. It harbors a thin sheet of material, less dense than the main rings, but far from vacant. The gaps and ringlets are sustained by gravitational resonances with Saturn's moons. When a ring particle orbits Saturn in a period that is a simple fraction of a moon's orbital period, such as 2 to 1, 3 to 2, or 5 to 3, the repeated gravitational pulls from the moon accumulate, either clearing the particle from the resonant orbit or concentrating it into a narrow ringlet. These resonances give rise to the intricate structures captured in Cassini's high-resolution images, a mesmerizing pattern of alternating bright and dark bands that, upon closer inspection, reveals an almost fractal complexity. Density waves, spiral patterns in the ring's surface density, driven by resonances with moons, ripple outward through the rings like waves across a pond. Bending waves, vertical oscillations of the ring plane, create corrugations that cast shadows during Saturn's equinox, when the sun illuminates the ring's edge on. During the 2009 equinox, Cassini captured stunning images of these shadows, unveiling structures that projected up to 2.5 kilometers above the ring plane, sculpted by the gravitational influence of unseen embedded moonlets. The rings also feature propeller-shaped disturbances, local clearings formed by small moonlets ranging from tens to hundreds of meters across, nestled within the ring material. These moonlets may be too small to carve out a full gap, but they are large enough to gravitationally deflect nearby particles, generating a distinctive propeller-shaped wake. Cassini identified hundreds of these propellers in the A ring and tracked several over the years, observing their migration through the ring material. And then there are the spokes, radial, dark markings that appear and vanish within the B ring, first noted by Voyager in 1980. Composed of tiny charged dust particles elevated above the ring plane by electromagnetic forces, these spokes rotate in sync with Saturn's magnetic field, rather than the Keplerian orbital motion of the ring particles. They seem to have a seasonal pattern, becoming more pronounced near equinox and fading during solstice. While their exact formation mechanism remains a topic of debate, they stand as one of the few instances in the solar system where electromagnetic forces visibly challenge gravity on a grand scale. The F-ring, a slender, intricately twisted band just beyond the outer edge of the A-ring, stands out as perhaps the most dynamic of all Saturn's rings. It is sculpted and contained by two shepherd moons, Prometheus and Pandora, which orbit on either side. Prometheus, the inner shepherd, periodically draws near to the F-ring, siphoning off streams of material and creating dark channels and bright kinks that evolve over mere hours. Observations reveal that the F-ring can change shape, form knots, and even appear to split and recombine, making it one of the most visually striking and least stable structures in the entire ring system. Within the A-ring lies the Encke Gap, maintained by the small moon Pan, a 28-kilometer body whose gravitational influence clears a 325-kilometer wide corridor in the ring material. Pan has gathered a thin ridge of ring material around its equator, giving it a distinctive shape reminiscent of a walnut or a ravioli. The Keeler Gap, also found in the A-ring, is upheld by the even smaller moon, Daphnis, measuring just 8 kilometers across. As Daphnis orbits, its gravity generates ripples along the edges of the gap, visible as scalloped waves in images captured by Cassini. These waves represent some of the most detailed examples of gravitational sculpting ever observed. A tiny moon, smaller than many urban areas, leaving its mark on a structure spanning 280,000 kilometers. The particles that comprise these rings are predominantly water ice, over 99% pure. Their sizes vary from microscopic dust to boulders several meters wide, with the highest concentration found in the centimeter to meter range. These particles collide gently at relative speeds of only a few millimeters per second, soft enough to bounce off one another rather than shatter. Such gentle collisions are crucial for maintaining the ring's flat, thin profile. Any particle that strays from the ring plane is nudged back by interactions with its neighbors. The rings effectively self-regulate. Their flatness is sustained by the same processes that, given enough time, would cause them to spread and dissipate. Each of these features, the gaps, the resonances, the density waves, the propellers, the spokes, narrates a story about the physics of disk systems. Saturn's rings serve as a natural laboratory for understanding the dynamics of flat, rotating, collisional disks. The same fundamental physics that governs protoplanetary disks around young stars, accretion disks around black holes, and the structure of spiral galaxies. Astrophysicists studying planet formation around other stars frequently use Saturn's rings as a testing ground for their models. The density waves in the rings are mathematically analogous to the spiral arms of galaxies. The viscous spreading of the ring material mirrors the viscous evolution of protoplanetary disks. The gap opening by moons directly parallels the gap opening by planets in protoplanetary disks. Indeed, the first theoretical models of planet-disk interaction were partly inspired by the Cassini division. In this regard, Saturn's rings are a cosmic Rosetta Stone, a nearby, accessible example of disk physics that can be examined in exquisite detail, offering insights that extend to disk systems throughout the universe. Losing the rings would mean losing this invaluable laboratory. Future generations of astronomers will have to explore disk physics without the advantage of the solar system's most beautiful and instructive example. The rings are not merely a visual marvel, they are scientifically indispensable, and they are vanishing before our very eyes. Saturn's system of moons is as diverse and scientifically significant as that of Jupiter. Titan, Saturn's largest moon and the second largest in our solar system, stands out as the only moon boasting a substantial atmosphere. This atmosphere is predominantly nitrogen, with a surface pressure 1.5 times greater than that of Earth, making it the only other place in the solar system where you could experience the sensation of air pressing against your skin without the need for a pressurized suit. Titan's atmosphere is rich in methane and other hydrocarbons, engaging in intricate photochemical processes that generate a dense orange haze, effectively shrouding the surface from direct observation. Beneath this veil of smog, the Cassini spacecraft and the Huygens lander, which successfully touched down on Titan's surface on January 14, 2005, unveiled a mesmerizing world adorned with lakes, rivers, and seas of liquid methane and ethane. Titan exhibits a hydrological cycle that mirrors Earth's water cycle, complete with methane rain, rivers, and lakes. The largest of these bodies, Kraken Mare, spans approximately 400,000 square kilometers, surpassing even the Caspian Sea. Remarkably, Titan is the only celestial body, aside from Earth, where stable, persistent bodies of liquid can be found on the surface. Beneath Titan's icy crust lies what is almost certainly a global ocean of liquid water, akin to those suspected to exist beneath Europa and Ganymede. The intricate surface chemistry of Titan, combined with its atmospheric organic compounds and subsurface ocean, positions it as one of the most intriguing targets for astrobiological research within our solar system. NASA's Dragonfly mission, a nuclear-powered rotorcraft designed to navigate Titan's dense atmosphere, is slated for launch in 2028, with an expected arrival in 2034. This mission will mark the first instance of a vehicle flying across another world's surface since the Ingenuity helicopter on Mars, but it will operate in a much thicker atmosphere and under significantly lower gravity, enabling it to carry an extensive array of scientific instruments for flights spanning kilometers. Dragonfly will hop from location to location on Titan's surface, sampling the organic-rich terrain and searching for signs of prebiotic chemistry, the essential chemical precursors to life. In many respects, Titan serves as a time capsule of early Earth. Its atmosphere is composed of nitrogen and methane, the same gases believed to have been present in Earth's atmosphere before the advent of oxygen. The ultraviolet-driven photochemistry generates complex organic molecules known as tholins, which fall to the surface, creating a thick coating of reddish-brown organic material. These very molecules may have been the foundational building blocks from which life emerged on early Earth. While Titan's surface cannot support life as we know it, given its frigid temperature of -179 degrees Celsius, far too cold for liquid water, its unique chemistry offers a glimpse into the processes that may have preceded life on our own planet. Moreover, beneath the ice and organic materials, Titan's subsurface ocean, warm, liquid, and potentially in contact with a rocky core, remains one of the most tantalizing targets in the field of astrobiology. If a form of exotic, non-water-based life could thrive in Titan's methane lakes, it would signify a fundamentally different biochemistry from anything we encounter on Earth. A second genesis characterized by an alternative solvent, distinct chemistry, and a unique evolutionary narrative. While this possibility remains speculative, it is far from impossible, and Dragonfly's instruments will be meticulously designed to detect anomalies in Titan's surface chemistry that could suggest biological activity. Enceladus, a small icy moon measuring just 504 kilometers in diameter, may very well be the most astonishing world in the Saturn system. The Cassini mission revealed that Enceladus is geologically active, with geysers of water vapor and ice particles erupting from fractures near its south pole, affectionately dubbed tiger stripes. These geysers contribute to Saturn's E-ring and hint at the existence of a subsurface ocean of liquid water lurking beneath its icy exterior. Cassini soared through the icy plumes of Enceladus, collecting samples that revealed a treasure trove of information. It discovered water, salts, silica nanoparticles, signs of hydrothermal activity on the ocean floor, and a variety of organic molecules. Notably, an analysis in 2018 uncovered complex macromolecular organic compounds with molecular weights exceeding 200 atomic mass units. This intriguing mix of liquid water, hydrothermal energy, and organic chemistry positions Enceladus as one of the most promising candidates for microbial life in our solar system. The revelation of Enceladus's ocean and geysers stands out as one of the most significant findings of the Cassini mission, an unexpected twist in our quest for knowledge. Prior to Cassini's arrival, Enceladus was dismissed as a small, frigid, geologically inert body. The discovery that it actively vents material from a hidden ocean reshaped our understanding of where life-sustaining environments might exist. Before this, the prevailing belief was that habitable conditions were confined to planets within a star's habitable zone, where liquid water could thrive. Enceladus shattered that notion. Here was a world, merely 504 kilometers in diameter, orbiting a staggering 1.4 billion kilometers from the Sun, in a region where solar heating is virtually non-existent. Yet it harbors a warm, salty, chemically vibrant ocean. This heat is not solar, but rather generated by tidal forces, the gravitational flexing of Enceladus's interior as it dances around Saturn in a 2-to-1 resonance with Dione. The ramifications of this discovery ripple far beyond our solar system. If a small body like Enceladus can sustain a habitable ocean through tidal heating, then subsurface oceans could be astonishingly prevalent throughout the universe. Not just beneath the icy crusts of moons in our own solar system, but also lurking beneath the surfaces of icy moons orbiting distant gas giants across the galaxy. The potential for habitable environments may be vastly underestimated, as we had been searching in the wrong places. Our focus was on liquid water on the surfaces of planets within habitable zones, while we should have also been exploring beneath the icy shells of moons in any orbit where tidal heating could provide the necessary warmth. Enceladus has rewritten the playbook. It did so simply because Cassini happened to pass by and observe geysers erupting from a moon that had previously gone unnoticed. Size is not a barrier to geological activity. The tidal heating, driven by the gravitational dance between Enceladus, Dione, and Saturn, supplies the energy that keeps its ocean in a liquid state and its geysers in constant eruption. Saturn's other moons are equally fascinating. Take Iapetus with its striking two-tone surface, one hemisphere gleaming like fresh snow, the other as dark as coal, adorned with a massive equatorial ridge that gives it a walnut-like appearance. Then there's Hyperion, an oddly shaped moon with a sponge-like, cratered surface that tumbles chaotically through space. Its rotation is anything but predictable, influenced by chaotic dynamics that render it one of the few celestial objects with genuinely non-repeating rotational behavior. If you could stand on Hyperion's surface, the sun would rise from a different direction each day, or perhaps not rise at all, depending on its erratic tumble. Iapetus is a moon that truly captivates the imagination. Its striking two-toned surface, one hemisphere gleaming like fresh snow, the other as dark as asphalt, has baffled astronomers since the days of Cassini, the astronomer, not the spacecraft, who first observed that Iapetus seemed to disappear when positioned on one side of Saturn and re-emerge on the other. The dark material coating its surface is thought to be dust collected from the Phoebe ring, a vast, delicate ring orbiting in the opposite direction of Iapetus, formed by impacts on the distant moon Phoebe. As Iapetus navigates through this debris, it gathers dark material on its leading hemisphere, which absorbs sunlight, warms slightly, and causes the ice to sublimate and redeposit on the trailing hemisphere. This creates a self-reinforcing feedback loop that starkly divides the moon into two contrasting halves, a phenomenon known as thermal migration. Moreover, Iapetus features a colossal equatorial ridge, a chain of mountains, some soaring up to 20 kilometers high, stretching along the equator for at least 1,300 kilometers. This ridge gives Iapetus a unique appearance, reminiscent of a walnut or a seam-sealed sphere. The origin of this ridge remains a mystery. Various hypotheses have been proposed, including the collapse of a former ring system around Iapetus itself, compression from an early phase of rapid rotation, or convective upwelling from the Moon's interior. No consensus has emerged. Meanwhile, Mimas, with its enormous Herschel crater, strikingly resembles the Death Star from Star Wars, and Phoebe, a dark, distant moon with a retrograde orbit likely captured from the Kuiper Belt, contributes to the vast, tenuous Phoebe ring that dwarfs all of Saturn's other rings in size. As of the latest surveys, Saturn boasts 146 confirmed moons, more than any other planet in our solar system. This moon system serves as a fascinating laboratory for exploring tidal forces, orbital resonances, surface processes, and ocean worlds. At the heart of this intricate system, feeding the E-ring, gravitationally interacting with the main rings, and shaping the orbital dynamics of the entire system, are the moons whose gravitational influence may have both formed and is now dismantling the rings. The Cassini mission stands as one of the most remarkable and impactful scientific endeavors in human history. Launched in 1997, the spacecraft reached Saturn in 2004 and dedicated 13 years to orbiting the planet, completing 294 orbits, conducting 162 targeted flybys of moons, and returning over 450,000 images. It carried the Huygens probe, crafted by the European Space Agency, which descended through Titan's atmosphere and landed on its surface, the most distant landing of any spacecraft to date. In its final months, the grand finale orbits provided groundbreaking measurements that transformed our understanding of Saturn's rings. On September 15, 2017, with its fuel nearly depleted, Cassini made a dramatic plunge into Saturn's atmosphere, meeting its end. A calculated sacrifice to prevent the spacecraft from inadvertently crashing into and contaminating Enceladus or Titan, both of which may possess conditions suitable for life. The spacecraft continued to transmit data until the very last moment, its instruments capturing the composition of Saturn's upper atmosphere as it descended. The signal was lost at 7:55 a.m. Eastern Time, when Cassini's antenna could no longer maintain its connection with Earth. At mission control at the Jet Propulsion Laboratory, the signal flatlined. Applause erupted, followed by tears. Engineers who had dedicated decades to building, launching, and operating the spacecraft stood in solemn silence. Project scientist Linda Spilker simply stated, "I'm going to miss it." The spacecraft had been transmitting for 13 years, 76 days, and several hours. During that time, it fundamentally reshaped our understanding of Saturn, its rings, and its moons. And then it was gone, consumed by the very atmosphere of the planet it had studied, its atoms merging with Saturn itself. The decision to end the Cassini mission was rooted in a profound commitment to planetary protection. Enceladus, with its hidden ocean and hydrothermal vents, is viewed as a potential cradle for life. If Cassini, running out of fuel and careening out of control, had collided with Enceladus, it could have inadvertently introduced earthly microorganisms which might have survived the journey. While the risk was minimal, it was deemed unacceptable. The same level of caution applied to Titan. By guiding Cassini into the depths of Saturn, a realm inhospitable to life, the team ensured that these moons remained untouched for future exploration. This act was not only a testament to scientific responsibility, but also a poignant farewell. After 13 years of orbiting Saturn, Cassini became one with the planet itself. Its atoms merged with the hydrogen, helium, and water in Saturn's atmosphere, perhaps even mingling with the water from the rings that was cascading down at the very moment when Cassini could no longer maintain its connection with Earth. The spacecraft had been transmitting data for 13 years, 76 days, and several hours. And then, it was no more. The data gathered during Cassini's final moments, the composition of Saturn's atmosphere, the mass of its rings, the flow of material from the rings to the planet, and the structure of the magnetic field between the rings and the cloud tops, continues to yield groundbreaking insights years after the mission concluded. The grand finale was not just a dramatic end, it represented the boldest act of exploration the mission ever undertook. Cassini's orbits took it through a previously uncharted expanse of space, the narrow corridor between Saturn's innermost D ring and the cloud tops. Before the first pass, no one could predict what challenges lay ahead. Would the region be littered with debris capable of obliterating Cassini upon contact? Would the magnetic field be so powerful that it would overwhelm the instruments? The initial dive on April 26, 2017, was fraught with tension. The mission team positioned Cassini with its high-gain antenna facing forward, serving as a shield against potential particles in the gap. For several hours, the spacecraft fell silent as it traversed this uncharted territory, cut off from communication with Earth. When contact was re-established, the data revealed an unexpected surprise. The gap was nearly devoid of material. The ring planet gap was cleaner than anticipated, almost empty of particles. Cassini had discovered a safe passage, allowing the subsequent 21 dives to proceed with the antenna oriented back toward Earth, facilitating continuous data transmission. During these final orbits, Cassini's instruments captured measurements that could only be obtained from this unique vantage point. The gravity measurements determined the mass of the rings. The magnetic field readings unveiled the deep rotation of Saturn's atmosphere. The in-situ detection of ring material descending into the atmosphere. The first direct sampling of Saturn's upper atmosphere. Each measurement was one of a kind, data that will never be replicated, as no future missions are planned to navigate this region. This marked the scientific pinnacle of the entire mission, the moment when Cassini approached Saturn closer than any spacecraft had ever done, returning measurements that could not have been acquired in any other way. Currently, there is no successor mission to Saturn on the books. NASA's Dragonfly is set to explore Titan, but no orbiter is slated to return to Saturn itself. The rings, in their current form, may remain unobserved by another spacecraft for decades. And when we do return, they will have inevitably thinned. Numerous concept missions to the Saturn system have been envisioned, each promising to unveil the mysteries of this majestic planet. Imagine a Saturn atmospheric probe, akin to the Galileo probe that ventured into Jupiter's atmosphere, meticulously analyzing the composition and structure of Saturn's deep atmosphere, including the elusive abundance of helium, a crucial element for understanding the phenomenon of helium rain. Picture a ring observatory, a nimble spacecraft in a close orbit, tirelessly monitoring the ring rain in real time, tracking the rate of mass loss and its seasonal variations. Envision an Enceladus Lifefinder mission, soaring through the moon's geysers with cutting-edge instruments specifically designed to detect amino acids, lipids, and other molecular signatures of life. Yet, despite these tantalizing prospects, none of these missions currently has funding. The next spacecraft set to grace the Saturn system will be Dragonfly, arriving at Titan in 2034. However, Dragonfly is primarily a Titan mission, not focused on Saturn itself, and it will not delve into the intricate details of the rings. A dedicated mission to study Saturn's rings would necessitate a fresh start, a new budget, and renewed political commitment, and the timelines of space exploration stretch across decades. By the time a future orbiter reaches Saturn, the rings will have undergone noticeable changes. The mass loss is a continuous process. The D ring may be significantly diminished, while the contamination level of the C ring will have escalated. The entire system will have evolved, dimmer, thinner, and edging closer to its conclusion. Each decade we delay is a decade of ring loss that we can never reclaim. When we finally return, the rings will have thinned, the ring rain will have persisted, and the conveyor belt will have transported more ice into Saturn's atmosphere. The rings we encounter next will not resemble those observed by Cassini. They will be a diminished version, a later chapter in a narrative that is already nearing its final pages. Now, let's step back from the dust measurements, mass estimates, and gravitational calculations and reflect on what it means to be alive at this moment. Saturn is 4.5 billion years old. For the majority of that time, approximately 4.1 to 4.4 billion years, it existed without rings. It was a bare gas giant, a pale gold orb banded with clouds, orbiting in the outer solar system, devoid of adornment. Then, perhaps 100 to 400 million years ago, a dramatic event unfolded. A moon was torn asunder, a comet was disintegrated. A collision unleashed a cloud of debris that spread, flattened, and coalesced into the stunning structure we observe today. And now, that structure is fading. Ring rain carries material into Saturn's atmosphere at a rate that will entirely consume the rings within the next 100 to 300 million years. The rings exist within a fleeting window, a brief interval in Saturn's extensive lifespan when ice happens to orbit in a flat disk around the planet's equator. This window opened recently and will soon close. And we, a species that has thrived for a few 100,000 years, that has wielded telescopes for 4 centuries, that sent a spacecraft to Saturn for 13 years, find ourselves here, right now, in the midst of that window. The odds of this coincidence are slim. Saturn has existed for 4.5 billion years. The rings have graced it for perhaps 200 million. The overlap between the existence of the rings and the emergence of a species capable of appreciating them is, at most, a few 100,000 years out of 4.5 billion, a ratio of about 1 in 10,000. We are witnessing something extraordinary, something ephemeral, something that the universe will not replicate in this specific form. This brings us to what some scientists have termed the ring timing problem. If the rings are young and fleeting, why are we fortunate enough to witness them? Is this merely a coincidence, or is there a deeper significance at play? One possibility is that it is simply a coincidence, a fortunate accident devoid of deeper meaning. The rings formed recently, they will vanish soon, and we happen to be here in the midst of it all. The probability may be low, but it is not impossible, and the universe is vast enough to encompass many low-probability events. Another intriguing possibility is that ring systems around giant planets may be far more prevalent than we currently think. Imagine rings being born and fading away throughout the life of a giant planet, formed by the occasional shattering of a moon or the capture of a wandering comet, only to be eroded over hundreds of millions of years, then re-established by the next cosmic event. If these ring systems appear and vanish over such extensive timescales, then at any given moment there's a reasonable chance that at least one giant planet in our solar system boasts striking rings. The timing conundrum becomes less daunting if rings are transient rather than permanent. A more speculative third possibility is that the very event that created the rings, the destruction of chrysalis, or whatever cataclysm scattered the debris, may have also influenced other parts of the solar system, potentially affecting the conditions that allowed intelligent life to emerge. While this idea is unlikely and lacks solid evidence, it highlights the fascinating questions raised by the ring timing dilemma. For now, the simplest explanation holds the most weight. We are fortunate. The rings exist, we exist, and both circumstances are fleeting, a ratio of about 1 in 10,000. We are witnessing something extraordinary, something ephemeral, something the universe will not replicate. This is what James O'Donoghue meant when he remarked, "We are lucky to be around to see Saturn's ring system, which seems to be in the midst of its lifetime." To call it luck is an understatement. We are the sole known witnesses to a phenomenon that has a clear beginning and an inevitable end, and our entire civilization occupies but a tiny fraction of its timeline. Every image captured of Saturn's rings is a snapshot of something that will not endure. Each observation is a testament to something that is, particle by particle, merging back into the planet it embellishes. The rings of Saturn are not a permanent fixture of our solar system. They are a moment, a breath, a fleeting glimpse of beauty in the vast expanse of cosmic time, existing just long enough for minds capable of grasping their significance to behold them. And we are those minds, the species that evolved from microorganisms on a small rocky planet within the inner solar system, that developed mathematics, telescopes, and rocket engines, that sent a spacecraft on a 7-year odyssey to a gas giant 1.4 billion kilometers away, and that discovered, in the final weeks of that spacecraft's journey, that the most magnificent thing it had come to study was in fact temporary. There's something both humbling and exhilarating about this realization. Humbling because the rings will not endure. Exhilarating because we are here to witness them. We did not arrive too early, before the rings came into being. We did not arrive too late, after they had faded away. We arrived at precisely the right moment, in precisely the right century, in precisely the right millennia, to behold the most spectacular natural phenomenon in the solar system at the height of its splendor. This is not a certainty, it is a coincidence, and like all coincidences, it is delicate. Had human civilization emerged 500 million years ago, we would have missed the rings. If it arises 500 million years from now, the rings will be long gone. Our window of observation is a sliver of time so narrow that, in the grand narrative of the solar system's history, it barely registers. And yet, here we are, looking up, witnessing the rings, understanding them, measuring them, photographing them, recording them for future generations, who may only know Saturn as a bare, banded gas giant, so they will understand what once graced the cosmos. Consider the broader implications of this for the universe. Saturn is not alone in its ringed glory. Jupiter, Uranus, and Neptune also boast ring systems today, delicate, dark, and faint compared to Saturn's, yet undeniably present. These rings could very well be the remnants of once mighty rings that have been eroded by the same cosmic forces currently at work on Saturn. If substantial rings are a transient characteristic of gas giants, formed from the destruction of moons and gradually fading over hundreds of millions of years, then the cosmos might be teeming with giant planets that once showcased breathtaking rings but now stand bare. The ramifications of this are profound. We might be experiencing not just a unique chapter in Saturn's saga, but also a pivotal moment in the solar system's narrative. An era when at least one giant planet still possesses a ring system grand enough to be deemed iconic. In a billion years, every planet in our solar system could sport thin, sparse rings, reminiscent of Uranus, or perhaps none at all. The age of magnificent rings may be drawing to a close, not only for Saturn, but for the entire solar system. This elevates the significance of Saturn's rings to a new level. They are not merely a stunning aspect of a single planet. They could represent the last great rings in our solar system, the final vestige of a phenomenon that was once widespread, that has been gradually diminishing for billions of years, and that will ultimately vanish. Saturn's rings are a remarkable gift, not born of intention or design, but rather from the blind, exquisite, indifferent mechanics of gravity and time. A moon met its demise. The remnants coalesced into a disk of ice. This ice captures the light of a distant sun and scatters it across a billion kilometers of space, into the lens of a telescope, into the sensor of a camera, into the eye of a being who comprehends, for the first time in the universe's history, what it is witnessing and how fleeting it truly is. Saturn's rings serve as a poignant reminder that beauty and permanence are not synonymous. The most breathtaking features of the cosmos are often the most fleeting. A supernova blazes brightly for weeks before fading away. A comet's tail glimmers for months, then dissipates into nothingness. An aurora dances for hours, then vanishes. And Saturn's rings, the most visually arresting structure in the solar system, will endure for only a few 100 million years in a cosmic timeline that spans billions. This impermanence does not diminish their value. If anything, it enhances their preciousness. A diamond is cherished partly for its durability, yet a sunset is revered precisely because it is ephemeral. Saturn's rings are the solar system's sunset, a phenomenon of breathtaking beauty that is, by its very nature, transitory. And like a sunset, they are best appreciated by those who understand they are witnessing something that will never be repeated. 4.5 billion years of planetary evolution, a few 100 million years of rings, a few 100 years of human observation, a few decades of spacecraft exploration. And throughout all this time, in all that vast, patient, indifferent cosmic history, one species on one small planet in the inner solar system gazed outward and beheld the rings. They understood them, they measured them, they named them, and they knew, with the bittersweet clarity that comes from scientific insight, that these rings would not endure. The rings remain visible tonight. They will be there tomorrow, and next year, and next century, but not forever. Nothing lasts forever, not the rings, not the planet, not the sun, not the species that gazes upon them. The only true permanence lies in the understanding itself, in the knowledge we have gained by observing, measuring, and sending a spacecraft named Cassini to orbit a planet called Saturn, revealing that the most beautiful spectacle in the solar system is also the most fleeting. 4 centuries ago, Galileo peered through a modest telescope and stumbled upon a curious sight. 2 protrusions flanking a faint disk, which he whimsically dubbed Saturn's ears. He was unable to discern the rings, and the true nature of what he observed eluded him. Fast forward to 1655, when Christian Huygens made a groundbreaking discovery. Saturn was encircled by a flat ring, tilted in relation to the ecliptic plane. Then, in 1859, James Clerk Maxwell mathematically demonstrated that these rings could not be solid. They were instead composed of an innumerable array of individual particles, each tracing its own independent orbit. By 2017, the Cassini spacecraft ventured between the rings and the planet, revealing that these particles, those myriad orbiting, glimmering ice fragments, have existed for less than 1/10 of the planet's lifespan and will vanish before another 1/10 has elapsed. From Galileo's whimsical ears to Cassini's poignant final transmission, the narrative of Saturn's rings mirrors the evolution of human comprehension, unfolding decade by decade, century by century, mission by mission. Each generation gained sharper insights, each new instrument unveiled greater complexity. Ultimately, the most profound truth the rings imparted was about their own existence. They are ephemeral, they are not eternal, and neither is our opportunity to witness them. In the distant reaches of our solar system, 1.4 billion kilometers from the Sun, Saturn rotates languidly in the cosmic void. Its rings capture the faint sunlight and reflect it back, a staggering quintillion particles of ice, each acting as a minuscule mirror, each orbiting at its unique pace, each gradually, imperceptibly spiraling inward toward the planet that will ultimately engulf them. The rings shimmer, the rings wane, the rings shed, and for now, in this fleeting, extraordinary, irreplaceable moment, they remain, still radiant, still magnificent, still ours to behold. And the more attentively we listen, the more they unveil.